have. So a force is a push or a pull on some mass that can change its motion. I can't spell today. Now there are a couple of different types of forces, okay? I don't know if we went over this specifically, but you could have something called, I'll write it in a different color, you could have an applied force. And I'm going to put this on Buzz. I've got like a nice little poster of all the different types of forces. So applied force, okay, we sometimes like to call F little a, that's our nickname for it, for applied force. So, for example, if I'm pushing on a box, I'm creating an applied force. Okay? If I am pulling on a rope, like in a tug of war, well, that is slightly different. Okay, so we'll get into that in a second. If a car's motor helps turn the wheels and push the car forward, that is an applied force. Okay? We also have friction. We're going to get into that down here in 1 second. So, Lydia, hi Lydia. So Lydia, I have a question for you about the lab we did, okay? So, oh, and I'm sorry, I should be looking here. I'm like looking at you on my other screen. So Lydia, when you increased, remember that bar for friction on the lab that you could like increase or decrease? Do you remember that or no? Okay. So what happened to the motion of an object when you bumped that friction up?
It slowed down.
It slowed it down. Bingo, and that's key. So if we go down here really quickly, we're going to skip around a little bit, okay? Friction is a force that always opposes the direction of motion. So, you know, for example, when that man in the simulation was pushing on that box was speeding up faster and faster, right? But when you increase the friction, that caused the box to maybe accelerate less or start to slow down. So the force of friction always opposes the direction of motion. And did anyone notice anything about the ground in the simulation when you increase the friction? For example, let me show you. I think it was this one here. Did you guys notice anything about the ground? Put it in the chat. Oh, I'm sorry, we're on page 56. Sorry, I forgot to say that. We're on page 56 of our book. I like jumped ahead a little too fast. So if we look on the simulation, if I'm increasing my friction a lot, look, the ground looks kind of like rough. But if I decrease it, it starts to look smooth or icy, right? So it's pretty smooth, and then it starts to get a little rougher and a little more textured. And that's what friction is essentially caused by, right? I'm not sure if I talked about it in this class yet, but when we're talking about friction between two objects, right? Maybe like a box and that ground, it's caused by the kind of like grainy textured material of the box sliding against the ground. So if we were to zoom in, okay, if we were to do a close-up here, we would have the textured material of the box. So this is the box. Rubbing against textured material on the floor. As you can see, the little nooks and crannies of the floor are going to kind of get caught in the material of the box, causing it to kind of like, I don't know, catch, if you will. That's what friction really is, at least between two objects. Okay? Now I said friction always opposes the direction of motion. Right? So if this is the acceleration of the object, if it's moving towards the right, the force due to friction is going to be moving towards the left. We're getting into something called a free body diagram, but we'll get into that later. So the force of friction is going against the direction of acceleration. And I also want you to notice, right, that the force due to friction, it's parallel to the ground. Remember parallel lines? They never intersect. They're at the same angle. So the force of friction, I'll add that. It's always opposed to the direction of motion and is parallel to the surface. I'm going to say if there is a surface. So if there is a surface, the force of friction is parallel to it. But as you can see, we've also talked about another kind of friction, and I know we've talked about this before because we've talked about free fall. We've talked about terminal velocity. And we get those two things because we have air around us. You can just whip your hand back and forth, all right? You can feel the air particles on your hand, okay? So we get air resistance because little air particles, gas, is actually hitting whatever's falling down. Same concept applies though, so let me show you. Let's say we have a ball falling downward. So here's our ball. Right, and it's accelerating downward, as objects tend to do during free fall. Guys, put it in the chat. What's the acceleration of any object in free fall? Remember this from last unit? Good. Should be 9.8 meters per second squared. So this is the direction of motion. I said that the frictional force always opposes the direction of motion. So what direction is friction going now? Put it in the chat. Is it going down? Is it going up? Is it going to the sides? Yeah. It's going up. Nice, Robbie. Nice, Azaria. It's going up. Because it is opposing the direction of motion. Again, remember this is caused because there's lots of little air particles, and when the ball collides with those air particles are pushing against the ball. That's what's happening. So we have friction caused by the surface, by a surface interacting with an object, sliding across it. We also get friction, right, because of air resistance. We also have something called the normal force. We call it F little n, right? Now it's called the normal force because in a higher level of math, normal means perpendicular, so at a right angle, okay? You can think of it in a right angle. So the normal force is always perpendicular to any surface, okay? And a normal force is a supportive force, okay? So if you think about it, I have this pen resting on my hand. Every single object on Earth is going to experience, right, that force due to gravity pulling it down, but we also have that normal force pushing it up, okay? So what's really interesting is if we go back to our simulation, right, and this man was pushing on the box, let me decrease the friction here. It's speeding up now. We have an applied force from the man pushing it. That applied force is moving to the right. We have a frictional force opposing it, moving towards the left. But what we maybe didn't catch the first time around, we didn't need to, oh, he let go, is we have that force due to gravity pulling the box down, plus we actually have the ground, let me stop this, we have the ground pushing up on the box, supporting the box. So that normal force is actually moving upward, right? Otherwise, this box would just fall through this kind of simulated floor, right? We also have a force due to tension. I'm running out of room. So we have tension. Call it F little t. Okay? And I don't mean like tension between friends. I mean tension physically. So if you were to play like a tug of war game, right, you're going to feel tension throughout a string or a rope. So that's the force due to tension. Okay. So now we went through forces, we understand what it is conceptually, we know a couple different forces. We're going to do a little post-lab. Okay? So I want you to turn to page 59, and we're going to start to figure out how our lab applies to something called Newton's laws. So I know, I'm sure some of you guys have probably heard of Newton's law. We're going to go all the way down to the bottom of this page. Again, this is page 59. You had a question similar to this on your lab. Okay? So I want you to put in the chat, what do you think the graph is going to look like when you plot acceleration compared to mass of an object that has a force applied to it? Explain what this is going to look like to me. Put it in the chat. This is based on your lab. You guys were playing with changing the acceleration of your simulation. You were playing with changing the masses. Nice. Exactly. I agree with a lot of the chats. We're going to see something like an exponential decay. Something just like that. Mathematically, what do we call this kind of relationship? Is this a direct relationship or an inverse relationship? Yes, yeah, Evelyn, it's inverse. So, as you can see, what that means is when mass is really small, when you decrease mass, you're going to increase acceleration. But when you increase mass, you decrease acceleration. Generally, an inverse relationship is you increase one variable, you're going to decrease the other. An inverse relationship. Now, what does the graph for acceleration versus force look like, right? What does that look like? If I increase my acceleration, what happens to my force? Put it in the chat. What is this one going to look like now? Nice, guys. Yep, you're getting it. So it's going to be a straight upward line. And, right, you're putting it already in the chat. This is a direct relationship. You saw this. This should just be review for you. You guys answered this already in your lab. This is a direct relationship. So again, if you increase acceleration, you see the force increases as well. Awesome. So based on what we're seeing in these graphs, based on that week we took on our simulation, we're going to start to develop an equation from the ground up. So what we can say from this graph here is that A, or acceleration, is proportional to 1 over m. Okay? So again, this little sign that looks like a fish, that means proportional to. That means it kind of correlates. It's a general relationship between these two. And if we look at our second graph, the relationship between acceleration and force, all right, we can say that acceleration is proportional to force, okay? So it says here we want to develop an equation, but we only have proportionalities right now. Guys, why do we want an equation? Why is it not enough to say, well, proportional is fine? Why is that not enough for us? Put it in the chat. Why is that not enough? Why must we try to develop an equation? Why do we like equations in physics class anyway? Yes. Awesome, Charlotte. Yes, Ian. It doesn't help us get numbers. It doesn't help us accurately predict what's going to happen. You can say generally, but we like to know things for sure in physics, and we can, and for that we need an equation, okay? So what we can do actually, well, we're going to create an equation, and we actually need an equation that combines both of these general proportionalities, okay? I can actually combine these proportionalities before I start to fabricate or build my equation. So I can actually combine these and say that acceleration is proportional to force over mass, right? That makes sense. It's directly proportional to force. It's inversely proportional to mass. This holds, guys. But to create an equation, we have to do one more thing. To take it to the next level, okay, we must say that acceleration equals some constant k times force over mass. This is how science is typically done, guys, which is really interesting, especially in chemistry, where chemists will see a relationship between quantities and then have to build an equation. They might not know exactly how they relate, though. K, this constant right here, proportionality, or this constant here, it could be equal to 1, it could be 2, it could be 3, we don't know yet. However, we do know one thing. We do know one thing. What are the units of force? We saw it in the lab. What are the units of force that we saw in the lab? Maybe we don't understand what they mean.
Newtons.
Yes, excellent, Preston. A Newton. We know that a force is equal to a Newton. So we know that forces units are newtons. I like to write it as an N, okay? Now a Newton is just like a really, this is a little different, I'm transitioning, but I promise it's going to make sense in a second, okay? 1 Newton is equal to a kilogram times a meter per second squared, okay? So this isn't a brand new unit, it's just a combo of units we've seen before. Now, what's very interesting right here, okay, is that this is mass, unit of mass, and this is the unit of acceleration, okay? Let's hold on to that for 1 second. 1 second. Probably said this slightly out of order. That's okay. It's okay. I'm going to tell you guys right now that this constant is 1. Okay? We know that A must equal F over M. Okay? So K is 1. I'm just deriving our equation right here. And what's really nice is now we can actually rewrite this equation. Before I do that, I just want you to know that right now, this equation will be the pinnacle of your high school experience, okay? You thought online learning was just gonna be kind of like a drag, all right? This is the pinnacle because this is one of the most important equations you may ever learn in your lifetime. It is responsible for why, planets rotate around stars. It explains why electrons move around a nucleus. It explains why you kick a soccer ball and it moves forward, okay? So get excited, because this is it. Force equals mass times acceleration. I want you to make it pop. You put a little box around it. And now I'm going to tie this equation that we've just derived. Remember, we went from just general proportionalities. We tried to create an equation with a constant. And I've told you that that constant is 1. Here's why. It's because, like Preston said, our units for force is a Newton. And a Newton is just a simpler way of saying a kilogram times a meter over a second squared. That means that it's only going to take that means that 1 Newton of force is the force needed to move 1 kilogram of mass with an acceleration of 1 meter per second squared. Right? And that's why we can just say force equals mass times acceleration. We don't need another constant, because they're all ones. 1 Newton of force, right, is going to accelerate 1 kilogram of mass with an acceleration of 1 meter per second squared. It's so beautiful when our math works out this way. And guys, that is Newton's second law. Let's pull what we just learned right now, and we're going to place it on our page. Jumping around. You have to jump around a little in this book. It's okay. We're going to go back to page 56. Back to page 56. Okay? This is the third kind of bullet point on this page, Newton's laws of motion. Newton's second law is a mathematical law, and it states what we literally just derived. That force is equal to the mass of an object times its acceleration. Now, we just talked about this a little bit, but I have a question for you all, okay? Now, if I were to increase the force a ton, 5 times, all right? But if I were to keep my mass constant, put it in the chat, how would my acceleration change? How would it change? Put it in the chat. If I increased my force by 5 times. Right, it would increase by how much? Can you put a number to it or an amount to it? Yes, it would increase by 5 times as well. So that's a big A. It's supposed to be a big A. It would also increase by 5 times because force and acceleration are directly related to each other. Good. Okay. Now, if I were to decrease my force, maybe by a half, and I were to keep my mass constant, how would acceleration change? Yep, it's a 1/2 the amount. So now it's a small acceleration. It's a tiny acceleration, exactly. The relationship. We can also state this mathematical equation, okay, verbally. Here it is. Based on what we know here, we can say that acceleration is caused by acceleration is related to these 4 things. So acceleration is caused by a force. You can see it in this equation. You need a force to have an acceleration. If force equals 0, you still have a mass. Well, acceleration has to be 0. Okay? So we must have a force in order to have acceleration. Point number 2. That acceleration is in the direction of your net force. We'll talk about net force later. In the direction about that because we already talked about net force, right, in our activity. How would you explain in your own words what net force means? Put it in the chat because you saw this in your activity already. Oh, it's okay, Robbie. How do you explain net force in your own words? Yeah, it's the sum of forces. So net force is the sum of the forces. Excellent. And just to make sure we're all on the same page when I'm talking about sum of the forces, let's just check out this brief illustration. You don't have to write this down. Say we have this box, just like in our simulation, right? And the man is pushing it, right? With an applied force, and it's accelerating in that direction. Okay? You can see my arrow is really big because this is a big force. But I also have friction, right? Maybe I had a tiny bit of friction. I'm going to put friction in pink. I had just a little bit of friction. It was going in the opposite direction because remember, friction opposes the direction of motion. Right? So it's moving this way. It's moving to the right. The big applied force is going to the right. The smaller frictional force is moving to the left. The sum of the forces, write this down. So the sum of the forces, which we also call the net force, right? That will be the force causing motion minus the force resisting motion, which is usually going to be friction. So if we're thinking about vector addition or subtraction in our case, right? We have our applied force of this length, and we add it right to a smaller force or a smaller vector this way, then that net force must be moving towards the right, smaller than the applied force. It's the difference between these two. So we can say that the net force is moving towards the right. And you guys, this is hopefully review, but hopefully maybe just a little more formalized because you saw this in your activity. Are there any questions about this? This says moving toward the right. Okay. So if we go back to page 56 now. We can tell then that net force was moving towards the right, right? Then our acceleration must be moving to the right as well. So acceleration is one more thing. Two more things actually. So point number 3. And we saw this on page 59 with our graphs, right? So acceleration is directly proportional to the force. And last but not least, maybe you're running out of room too, acceleration is inversely proportional to mass. is Newton's second law? Why did we hit Newton's second law before the first law? You may ask yourself, because we're not starting from the beginning of Newton's laws. That's because I really thought that the lab we did kind of hooked best into the second law. What's interesting though is that the second law and the first law of Newton's three laws are actually kind of the same. They're saying the same thing. Okay? And the first law is all about inertia. We already talked about inertia, didn't we? Did we talk about inertia already in this class? Give me a thumbs up if you've got kind of the definition of inertia written over here. No, we didn't. Nope. Okay, that is fine. That's actually pretty good. That's great. Okay. So I'm gonna do some demos of this next time, just because we have a little extra time left. Why don't we just go for it? I'm gonna erase some of this so we have some more room. Again, I'll post a video of all of this. So Newton's first law states this, okay? So it's called the law of inertia. And we're going to have to define that, right, up at the top of the page. So the first law states that an object that is moving at a constant velocity is going to stay at that constant velocity. Unless it's acted upon by an outside force. And I'm guessing quite a few of you have maybe heard of something similar. So say yes or put your thumbs up if you've heard the definition: an object at rest will stay at rest unless acted upon by an outside force. Have you heard that before? Yeah, right? Some of us have. But I don't think that that's accurate, okay? Because if I'm not moving at all, right? If I'm at rest, that's 0 meters per second. Well, if I'm at rest now, have I changed speed? If I'm at rest now, have I changed speed? Time's gone on, but I'm still at a constant velocity of 0 meters per second, okay? So this definition includes rest. But the issue with that first definition, an object at rest will stay at rest, is that it leads to a misconception amongst physics students, right? And that misconception is that an object that's moving at a constant velocity does not follow this. Well, that's not true, okay? And maybe you saw this, right, in your simulation. I can show you. So if you have like a super icy surface, right? And if you apply force but then let it go, come on. It's still going to keep moving forever. There's no opposing force here, okay? It's just moving, it's moving, it's moving, it's moving, it's moving. Okay? It can keep moving. There's no force applied anymore, right? Because there's no force on one side, there's no force on the other side, okay? You could have also had this scenario, right? Where you maybe had equal and opposite forces on each side, but it was still moving. right? You might have seen that too in your simulation. So therefore, Newton's first law includes objects at rest and objects at a constant velocity are going to keep doing their thing unless they're acted upon by an outside force. Now, I mentioned this thing, law of inertia, okay? So what is law of inertia? Well, let's demo it right now. And I have to get that simulation back up. Should not have done that. So I have a quick question for you all while I get this up. I'm guessing you guys did some experiments, right? Where maybe you used like a light crate and then tested like a heavy refrigerator. What did you notice about trying to make those two objects move? Was one harder than another? I should see like a bunch of yeahs, right? Right, so if I like apply 100 newtons, right? This is moving just fine, everything's great. But if I apply the same force to my fridge, it's barely moving. That was one of the questions on the first page. It's much harder to move a mass that's larger than a mass that's smaller. And that is what the law of inertia, or that's what inertia basically is, right? Inertia is a property of matter, okay? Objects of higher mass are going to want to continue to stay at rest or doing whatever they're doing. It's harder to change what they're doing because they have a higher mass. Like it's harder for me to push a fridge than it is for me to push maybe, I don't know, my physics book across the table. Right? So it's a property of mass. We've got one more minute. So inertia is a property of matter. Essentially, the higher the mass, right, the more resistant it will be to a change in motion. Just like that heavy fridge. So I can condense that down to one thought. And that's that inertia is essentially a property of matter that quantifies an object's resistance to a change in motion. I'm not talking about friction here. I'm talking about the mass of an object. We're going to do some demos next time we meet to really like clarify what I mean by this, okay? And then we'll get into Newton's third law. Hope you guys have a great rest of your day. I'll see you next time. Thank you. And I will post a video of this on Buzz. Thank you.